Hi, I am Mr. True. In this video and the next, we're going to learn about a test that we can apply to categorical data. This will be the first time in Intro to Statistics that we've not worked with categorical data. We've talked about conditional probabilities before and looked at two-way tables, but the chi-square test is going to be our first test that we can apply to that type of data. So let's get started. A chi-square goodness of fit test will answer this kind of question. How well does a categorical sample distribution fit into a hypothesized population distribution? Well, this kind of question can be answered by the chi-square test for goodness of fit. That goodness of fit name for my textbook, hopefully it's the same for all, is reserved for when you're working with a one-way table. Real popular example is about if the percent, like M&Ms come in different colors, red, blue, brown, whatever, green, they supposedly create those M&Ms in a particular distribution, what percent are red, what percent are yellow, and so on. Well, if you collect a sample, you can see how well or if that sample fits the company's claimed distribution. I've made up my own example for this video since I'm publicizing on YouTube, but that's a common example. We will be doing a chi-square test for two-way tables as well, and we just call that inference for a two-way table, and I'll talk more about that in the next video. Okay, the formula for calculating chi-square, which I see I've had a little bit of added graffiti to my formula here. Chi-square is equal to the summation of the observed values minus the expected values squared divided by the each individual expected value. And let's not forget this Greek symbol for summation just means constantly add. So we'll do this particular calculation for every cell in the one-way table and then add up all those results. The degree of freedom for this test is k minus 1, where k is the number of cells. So it's not about how big the numbers are in the table, it's about how many cells or what size that table is, that categorical table. The conditions for doing a chi-square test is that all of our counts, all of our expected cell counts are at least 1, and no more than 20% of the expected cell counts are less than 5. Now, depending on what kind of calculator you have, with the one-way tables, with older calculators, you'll have to do some of this work by hand. And then in the next video, when we get to the two-way tables, we're pretty much going to let the calculator do almost all of that work, and we just interpret the numbers. So even though there's a condition to doing a chi-square test, these expected cell counts you may not actually know them until you apply the test or have the calculator or computer do the test for you. And then you come back and you check your condition. We can always calculate our own expected values, but that's not something that we tend to really care to do because it's time consuming, and hey, if the calculator computer can help, why not let it? Next screen. Now, you may see a lot of percents in these problems, but you're only going to do the test with the count values, not the proportions or percents. So, if you have a lot of percents in your problems, make sure you work out those count values and put those into your calculator or computer. The process is slightly different between one- and two-way tables, as I've already discussed, and we're only going to do a one-way table in this example. Now, before we start the example, even though it sounded like I just was about to, we do set up H sub O, assuming there's no association, and that kind of language is going to be appropriate for the first example that I do on this video, but it's really more for your two-way tables. Is variable A along the top of your table and variable B along the columns, or down the side of your table, are they related or not? Is there any association? So this language is a bit more for two-way tables, but it can still apply for a one-way table. Or, does your actual population fit the hypothesized population, or are the proportions equal if that's what you're looking at? H sub A, there is an association. Again, this is language more for the two-way tables, but occasionally can be applied for your one-way tables. Or, is the actual population, does it not really fit the hypothesized population? Or is there at least two of the proportions different? Because if 1% is higher, another percent is going to have to be lower, so they still add up to 100%. So that's your thoughts as far as how you set up H sub O and H sub A. let's actually look at the example and get to crunching some numbers. Here's our example we're going to take a look at in this video. Is there a relationship between the day of the week and the number of ER visits to the hospital? Now, because of space was limited, this would go on and talk about how data was collected over a few months' time and, blah, 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 blah. But H sub O is the ER visits are equally likely each day of the week. My problem doesn't say anything about, it doesn't hypothesize, or it's not a company claiming that, or a hospital claiming, this is what percent of our ER visits are on Sunday, Monday, Tuesday, and so on. It just says, is there a relationship? So we're going to assume that each day is equally likely. Remember, we set up H sub O as either there's no association, so it'd be like no association between the day of the week and whether or not somebody comes into an ER for a visit, or it's, that your observed population distribution or sampling distribution, fits well into the hypothesized population distribution. And then H sub A is that the ER visits do differ from day to day, or that our observed distribution does not fit the hypothesized distribution. So over the 3 months of collecting data, we have these count values for ER visits during the week. So Sunday, Monday, Sunday through Saturday, and we have the counts of 823, 768, 747, 729, 794, 837, and 877. Now, we would call this a one-way table. There's only one row of data, and we're looking at the number of ER visits per day of the week. Because we only have a one row of data, this is a one-way table. Older graphing calculators do not work with these easily, so we will do this work, kind of by hand with an aid of a calculator, as opposed to just, see, with a newer TID4 with the new software, or the TI Inspire, they'll do this process a bit more automatically. You will still have to find your own observed values, or expected values, but they will do them more automatically than, say, a TID1 or a TID3. So we're going to do this example as if you have an older calculator that will not do this test for you almost completely automatically. And if you do have an Inspire, I'll be posting a video up about how to do this with that calculator. Now, as we look at these numbers, it does seem like there is a higher count for Friday, Saturday, and Sunday. But if I could just look at the numbers and go, yep, weekend days have more people going to the ER. Maybe sports game accidents, drinking related problems, fell off a ladder when you're doing some house repair. But if all I could do is just look at these numbers, I wouldn't need to be in a stats class, right? So let's start crunching some numbers. Now, if you take all those observed values that I just had on our problem, it came up to be 5,574 observations, or ER visits. So we're going to take each of those count values and divide them by 5,574 to get a percentage of visits. So on Saturday we had 14.8% of all visits to the ER. Monday representing 13.8% of all the visits, Tuesday 13.4%, Wednesday 13.1%, and so on. We're not going to use these percents in our calculation of chi-square, but we will refer to them back later when we do the conclusion statement if it is determined that there is a relationship between the day of the week and the frequency or the possibility of an increased possibility or change in the probability of someone going to the ER, or count value. We will use these. Okay, I just said that. Okay, we're going to calculate the expected cell counts for each of those cells in the table. If there is no association between the day and the number of ER visits, the probability for each day is 1/7, or we should be seeing that 14.3% of all ER visits occur on every day of the week. So we're going to take the expected, we're going to find these expected values by doing 1/7, or 0.143, and multiplying it by the number of total observations, which was, again, 5,574. This comes up to an expected cell count of 796.3. So the expected cell count for every one of the 7 days of the week is that same value of 796.3. and thus I've written it. Okay, so we have our observed count values, we have our expected count values. Let's actually run through the formula of calculating the chi-square statistic and make sure that we do include the condition check and draw a conclusion based on the observed p-value and the h sub o and h sub a. Next screen. The calculation. Again, chi-square is the summation of the observed minus the expected cell counts squared divided by the expected cell count. And then you add up all those values. Well, the conditions, as we saw on the previous screen, all of our expected values are greater than or equal to 1, and no more than 20% are less than 5. I'm just going to rephrase that check. And I've got the expected cell counts, right next to this check, or right above it, or right below it. So clearly, I've actually, gone through. You don't need a big, long, wordy explanation of that. Just restate the condition you're given, write the expected cell count somewhere near there, and you're done. Now, this is what you would want to do to calculate chi-square with an older calculator, an TI-83 or older, or a TI-84 without the updated software. You put those observed cell counts into list 1, you put the expected cell counts into list 2, you put your cursor, you're in the stat edit menu, by the way. Stat, edit, go to your tables. I'm sure by now in this level of statistics you've used that window or that screen on your calculator many, many times. You put the cursor on the L3 name of the third column, and you'll be typing this in. It'll show up, the type will show up at the bottom of the screen. You'll be typing in parentheses L1, your observed values, minus L2, which is where your expected values are, close the parentheses, square it, and divide it by L sub 2. Now, then you'll exit that window with those values in list 3, and then go to the home screen of your calculator and just go to second list, go to the math operations menu, and look up sum, and just add up the list 3. And in this case, we have a chi-square value of 21.03, a degree of freedom of 7 minus 1, which is 6, and that translates into a p-value that's between 0.0025 and 0.001. Those are very, very small p-values. So our conclusion is going to be, with such a small p-value, there's very strong evidence for h sub a. That means that there is a relationship between the number of ER visits and the day of the week. Now notice I didn't describe what the relationship was. With chi-square, you're just looking for, is there an association or not? H sub o is that there is not, H sub a is that there is a relationship. Or, again, H sub o, does the observed population fit the hypothesized population distribution? Or H sub a, does it not? It's not so specific. There's no such thing as an example as a one-sided test where you look for the shading to the left, or a one-sided test where you shade to the right. It's just, is there an association or not? So it's kind of like, relates to a two-sided test, a regular two-sided hypothesis test for a z-score or t-score. Now, by the way, I forgot to include a drawing here, didn't I? All chi-square distributions are going to be what we would look at as being right skewed. So this chi-square statistic of 21 is out here somewhere, and our tail area is this very small area, again, between 0.025 and 0.001. So again, I'm talking about with such a small p-value, I'm using the actual size of the probability of observing this event, or one more extreme, and then relating it to the original H sub o and H sub a statement, and that we do have strong evidence for H sub a. All your summary statements after a significance test must use the value, your p-value, and then refer it to whether you have evidence for H sub a or you don't have evidence for H sub a, or you reject H sub o, or you fail to reject H sub o. Now, we did look at those percent, so I have one more sentence here. There's a higher proportion of visits on weekdays or weekend days, I'm labeling that as Friday, Saturday, and Sunday, observing percents in the range of around 15%, whereas the other days, Monday through Thursday, have percent values, proportions of ER visits somewhere between 13 and the low 14% range. So I'm using those observed proportions to then describe what relationship I see after I've determined with my very small p-value that there is evidence of that association. So again, you make those observed probabilities or those observed proportions, but they do not come into play until you can say that you have evidence for H sub A, that there is that association or that your observed distribution, your observed population does not fit the hypothesized distribution. Bam! Bam! Last example. We're going to put a small tweak on our previous work just to see how our H sub O and H sub A statement would look if we were given an actual hypothesized distribution instead of just is a relationship between the day of the week and the number of people going into the ER. Just see what the language would look like. And it's a very similar problem, so I'm not going to break it down piece by piece. I'll verbally go through this some, and hopefully you can come up with this. Chi-square is equal to 12.1, and our p-value is 6% on your own. And if not, watch the first example again. What would it look like, what would H sub O and H sub A look like if your example said, the hospital claims that Friday through Sunday, we observe 15% of all of our ER visits on the individual days, and then on Monday through Thursday, we observe 13% of all of our ER visits, again, on those individual days. Well, H sub O is that the distribution of visits fits the hospital's claim distribution, and H sub A is the distribution of visits don't fit the hospital's claim distribution. And again, we have our observed values on Sunday through Saturday. We have our observed values of 823, 768, and so on. These are the same ones we had before in the previous example. But here, our expected cell counts are not all equal, because we're not just looking for a relationship between day of the week and ER visits. We have a claim that, again, Friday through Saturday sees 15% per day and of all visits, and Monday through Thursday sees 13%. So our total observed count of 5574, that's the total number of visits we had at the ER, well, that times 15% is 836.1, and so thus you see the same expected cell count for Friday, Saturday, and Sunday. Now, for a Monday through Thursday, we're doing 5574 times 13%. Well, now we have a list of observed values, we have a list of expected values, and regardless of what kind of calculator you have, new TI Inspire or old TI 81, 82, 83, whatever versions are out there, you need at least this much. Now, again, new calculators, you can put these in there, boom, get your answer immediately. Older calculators, go to your stat edit window and do the calculations like I showed you on the previous screen. You should get a chi-square value of 12.1. Your p-value, now I've calculated this exactly from my calculator, comes out to be a tail area of 6% and a degree of freedom of 6. So my summary statement would be for this, well, my p-value of 6%, that's the probability of observing a chi-square statistic of 12.1 or more, one more extreme, one closer to the tail, is 6%. So I would say there was, pretty weak evidence against H sub O. Now, if your question has a level of significance set at 10%, you might say, well, 6% is lower than the alpha or the level of significance of 10%, so we reject H sub O. But I think that's a somewhat large p-value, so if anything, I might say there's weak evidence against H sub O. That we found, our observation does not fit the company's claim, but, or you might say that there is very little or no evidence against H sub O. It depends on what you feel is a good statistical significance level. And again, no level of significance is stated, so I'm not going to draw a hard line of reject H sub O or fail to reject H sub O, but again, 6%, I'd say pretty weak evidence against H sub O. So we will not, well, reject it if we do have that level of significance. So, I'm Mr. Tarrou. That's our first video for doing a chi-square test, a chi-square goodness of fit test. Bam! Go do your homework. Thank you very much for watching.